Today, we will be talking about this amazing new paper released by Meta on Byte Latent Transformers. This paper proposes some very educational, smart, and honestly pretty genius new innovations for training language models. We will be talking about what these major innovations are, how they each work, and why they might drastically improve the task of language generation with large language models. As usual, I have tried to distill the most important takeaways from this paper into visual diagrams that I hope will help you to understand the concepts in this paper at the most fundamental level. The deeper you get in this video, you will be absorbing the deeper truths and a more detailed intuition of this paper. So I hope you do watch it till the end. Without further ado, let's start at the basic overview of what this paper is all about. Welcome to Neural Breakdown. You are magnificent. So there's a lot to discuss. So where do we even start? Well, why don't we start at the title of this paper? Byte Latent Transformers, patches scale better than tokens. Believe it or not, understanding this title itself will tell you the entire point of this paper. So let's break this title down one word at a time, and I promise the whole picture will unfold. First off, this paper extends upon the classic transformer architecture. So that word definitely takes the center stage in this title. You can apply the concepts proposed here in just about any type of transformer architecture. Encoder, decoder models, encoder-only models like BERT or vision transformers, and of course decoder-only models for language generation like GPT and other modern LLMs. We will largely be discussing the language generation use case since that is the main focus point of this paper. But as you're watching this video or reading this paper, be aware that the concepts you learn here can be transferred to other transformer-based architectures with some minor tweaks as well. So traditionally, to train a language model, we teach it the task of next word prediction. Given an input sentence, we split these sentences into words or subwords and pass them through a series of causal attention layers to predict the next words corresponding to each input. The splitting operation right here for breaking down the sentences into these smaller components is called tokenization. The input of tokenization is a sentence and the output are tokens. At the bottom of this transformer tower, all tokens are independent of each other. They have independent embeddings, meaning they are not really connected with each other or dependent on each other in the sequence. Each causal attention layer contextualizes each of these independent tokens with all the tokens that have appeared previous to it. The term causal basically means that this network uses past values to predict future values in the sequence. So in this example, the representation of the token predict is composed from the representations of the words LLMs, learn, and to. You can imagine that each of these final representations at the end of all of these layers are representations for each prefix in the sentence. The magic of attention is that each layer can work parallelly across the entire sequence, meaning they process all of the tokens in the sequence at once while still maintaining the causal dependencies. Anyway, so that's transformers. Next, let's talk about another word that appears in the title, tokens. So we have already talked a bit about what tokens are. They are a sequence of these entities that we have split up our original sentences into before the transformer model processes it. Way back around early 2010s, the most popular way for tokenization was word tokenizers. These simply split up the sentences by the white spaces that appear in those sentences. A more common approach these days is to do subword tokenizers. Given our training data, we find the most common words or subwords in our corpus often through a technique called byte pair encoding. Say we would find the 5,000 most common subwords in our training dataset and construct a fixed vocabulary with these subwords. Given a new word, we would check if our vocabulary contains the complete word, but even if the complete word is not present, we would simply break it up into a sequence of subword tokens that are present in our vocabulary. But of course, to input these tokens into a machine learning model, we first have to convert it into a numerical representation, because obviously neural networks don't really see the text form of it. They want a representation, a vector representation of these tokens. So for that, next we will randomly initialize an embedding vector for each token in this vocabulary. This is often referred to as the embeddings table, which is simply a lookup table to fetch the representation of a specific token. Both the number of tokens in the vocab and the size of the embedding vectors are hyperparameters that we choose at the start of training. So let's say the embedding size we pick was 256. To initialize this embeddings table, we simply initialize a random matrix of shape 5000 by 256. And after we split the sentences into the subwords, we will simply look up the index of the token in the vocabulary and replace the token with the embedding from the lookup table. We do this for each token, and now we get these dense numerical vectors to represent each token. We call it dense because you're using just 256 continuous values to represent 5000 words. Also notice that since the embeddings lookup table is randomly initialized at the start of training, they won't actually represent each token in the beginning. But the intuition is that once the network is training, we will backpropagate the losses all the way back to the embeddings table. At the end of the training, these embeddings will indeed be representative of the words. There has been some old research papers from way back in 2013 that have indeed shown that the embeddings sort of arrange themselves in a semantically relevant way. Like similar words get mapped into the same areas of this 256 dimensional space, while dissimilar words get mapped away from each other. I have an old video on the channel called The History of NLP that does explain how word embeddings work in a bit more detail. So if you're interested, go check that out. So we have talked a bit about tokens and especially tokenizers. We are still building up to Byte Latent Transformers, and these concepts are very important to understand to appreciate why the Byte Latent Transformers even exist and what problems they're trying to solve. And let's talk about what problem they're trying to solve in the next section when we discuss the word scaling. So in the next section, we'll get into the meat of the problem and explore how changing the vocabulary size impacts the complexity of a language model. This right here is the key essence of this paper and the main reason why this paper even exists and what problem it is trying to solve. Ready? Pay attention. Suppose your vocabulary size is 5000 as before, and our chosen embedding dimension was 256. During the forward pass through the transformer, each causal attention layer will output a 256 dimensional context vector for each token. At the end of the network, however, we want to project the output back to the vocabulary space because we want the network to predict the final tokens, right? So the last layer of the network therefore will consist of something called as an unembedding layer that maps this 256 dimensional dense representation back to a 5000 dimensional probability distribution. In other words, if the output of the last causal layer is shaped as n by 256, where n is the number of tokens in the sequence, we must multiply this matrix with a trainable weight matrix of shape 256 by 5000 to get the new n by 5000 representation. Finally, by applying a softmax on this, we will convert each row into a probability distribution, which means that each row will now tell us the probability of the next token given the input sentences prefix. So if the 14th index of the second token has a very high value like 0.9, the network is trying to say that the 14th index of the vocabulary has 90% probability to appear as the next word on the second index. So to understand the essence of this paper, let's dig a little bit deeper to see how changing the vocabulary size will impact the number of flops or floating point operations in the network. Remember, higher flops simply means that the transformers is burning more compute to get the job done. Let's say you increase your vocabulary size from 5000 to 50,000. Well, a lot of new words are now in your vocabulary. What does this mean? Well, this means that the chances for a specific word to just exist in the vocabulary is now much higher. Words that earlier used to maybe be split into 3 tokens may now split into just 2 or even 1 token. This means that the number of tokens in the input sequence will go lower because the granularity of your tokenization is now much higher because you have more words in your vocabulary. So the transformer graph will get executed less number of times because the average sequence length will be lower, and common intuition will suggest that this will decrease the number of flops, right? Well, there's a catch. A larger vocab also means that you have to store a much larger embeddings table now, and maybe the 256 dimensional vectors won't be able to powerfully distinguish between each word anymore. So you may have to also increase your embedding size for better performance. Larger embedding size will increase the number of flops because things that used to be a 256 dimensional vector math is now 512 dimensional vector math. Also, the last layer of the network will need to do a larger matrix multiplication for each token. What earlier used to be a 5000 by E weight matrix will now be a 50,000 by E weight matrix. More flops during forward propagation means more gradients, and more flops during back propagation to update the additional weights. The point is that increasing the vocabulary has a dueling effect when it comes to the flops. Like, on one hand, it might decrease because the sequence of tokens got lower, but it may also increase since the computational force required for each token has also gotten higher. There is a scalability dilemma here with every type of tokenization strategy. The paper title says patches scale better than tokens. A little bit later, we will see what they mean by patches and why they're supposed to scale better than tokens. But before that, we have to talk about the first word in the title, byte. So far, we have considered words and subwords as our tokenization level. But what if we do it based on characters, where we split up a sentence based on the alphabets? Well, better yet, suppose you want to also input images or audio into the network, and obviously you can't split those into characters. So maybe instead of saying we'll split into characters, we can say we'll split them into bytes. Bytes are universal. Any data you store on your computer can be represented as a byte stream, be it a text file, an audio recording, an image. Everything can be split up into bytes, and we know that can be represented in 256 values. So all types of data can be broken up into a stream of bytes, and each byte can have 0 to 255 or 256 values. As an example, if you have the character capital A, you can say that its byte encoding is the number 65 because the ASCII of capital A is 65. This type of splitting is called a byte tokenizer. And the cool thing about a byte tokenizer is that you don't need a separate vocabulary for this. You already know the 255 values that a byte can take, so you already have access to the vocab. You don't need to find frequent words or anything of that nature anymore. And there are some great advantages of using this type of a byte tokenizer. Well, one, you don't need to extract vocabularies from your training data. Number two, bytes are agnostic of the underlying language. Number three, there are no worries about invalid or out of vocabulary tokens. Number four, bytes are compact representations, so the number of total embeddings you train is much smaller. In fact, it's fixed at 255. Bytes are multimodal, meaning you can use it basically for text, audio, images, or any type of data that you can store in memory. On the flip side, there is a huge disadvantage as well. They produce longer sequences because you are splitting up each word into the smallest possible unit. This will increase the number of flops way too much, making generation extremely slow and prohibitive to use in most real-world use cases because the sequence length can be way too long. And for that reason, byte-based encodings have never really been able to replace subword tokenizers for training language models. When we use subword or word tokenizers, we are doing a kind of grouping or clustering where we are combining the representations of semantically relevant contiguous sections of the bytes together and then passing that into a network as its own token. We inform the neural network that these entities have a special meaning, so they're grouped together. So that has also been a challenge to actually extract performance from these byte-based tokenizers. But even if you solve that, clearly passing a large sequence one byte at a time is not going to scale very well at all, especially for really large language models. Until now. This BLT paper indeed makes byte encoding a possibility, opening up all of those advantages that we talked about earlier. Multilinguality, multimodality, vocabulary-free training, and to understand how it achieved this, let's now talk about the next significant piece of this puzzle, the term patches. Also, if you're enjoying this video, please do hit the like button, say something in the comments, subscribe to the channel, and of course, if you want to support us and get access to all of the slides and documents that went into producing this video, you can join our Patreon. Our Patreon is growing at a pretty healthy rate, and I'm very thankful to everyone who is supporting the channel this month. Thank you. Go check out our Patreon. It is awesome. So what is a patch? Well, a patch is just a collection of contiguous bytes. Given an input sentence, BLT first extracts the byte stream from the text as discussed earlier. Then it uses a simple neural network to find the boundaries where this byte stream can be grouped into separate patches. This neural network is called the Entropy model, and we will come to this in just a minute. Once we find the patch boundaries with the help of this entropy model, we can go from a byte representation to a patch representation. Obviously, since a patch is a group of bytes, the number of patches in a sentence is much lower than the number of bytes in a sentence. This smaller sequence of patches is inputted into the transformer instead of directly inputting the longer byte stream. And that's the key point, that the transformer model operates only on the patch sequence and not directly on the byte sequence. Since there are lesser number of patches, the computation required for each invocation of the transform model is also much lower than if you use the longer byte representations. So you might think that, dude, patches are the same as subwords. Subwords are also a group of bytes, right? But there's a difference. The big deal is that the subword tokenizers learned a fixed vocabulary and they split up sentences based on that vocabulary. The tokenization in subword tokenizers do not depend on the complexity of the input sentences at all. It only depends on the preprocessed vocabulary file. The difference with the patches in BLT is that a neural network helps to do this patching, and it is sentence dependent. By using the entropy model, the grouping of different bytes is dynamic, meaning it depends on the sentence itself. There is no additional vocabulary here, so depending on the sentence, the entropy model could decide how to patch it, including grouping across word boundaries. So what is the entropy model? And while we're at it, what is entropy? Well, simply put, when something is less predictable or more uncertain, it has high entropy, and when something is very predictable, has low uncertainty, it has low entropy. Suppose you as a human need to predict the next alphabet for the prefix John's two favorite subjects are dash. Well, the next alphabet could be anything. If you draw the probability mask over all of the 26 characters in the English language, the probabilities will be rather uniform because a lot of subjects start with the letter A, C, M, P. Well, not many subjects start with the alphabet X, Y, so maybe those probabilities will be low. But at this point, there is high uncertainty about what the next alphabet would be, which means that the entropy is now high because the prediction space is more chaotic, where multiple alphabets could be possible. What if now I let you know that the first alphabet is M and ask you to predict the next alphabet from this new sequence? Well, now the entropy is a bit lower because you have more information. The next alphabets could be A for math or machine learning, or the next alphabet could be, I don't know, E for mechanical engineering or medicine or something like that. Now, what if I told you that the next two alphabets are A and C? Well, now you got more information. You are less uncertain. The entropy is lower because you can guess this is probably machine learning. So the entropy of H and I and N are all very low because the prediction space has now gotten much simpler. There is one clear alphabet which is winning. After predicting machine learning, the entropy rises again because if you add the word and, you now have to predict John's second favorite subject, which is once again very hard to do without more information. Again, high uncertainty at this point, high entropy. But once you know the next alphabets are MA, if I told you that, the entropy drops once again and you can figure out that the word could be math. Importantly, the fact that you have already predicted machine learning before will inform you further that there's very little possibility that the next word would again be machine learning. So it's either math or mathematics or something like that. The previous information is directly impacting the entropy of your current prediction. Well, predicting that is exactly what the entropy model is trying to achieve. The entropy model is a very small transformer-based next byte prediction model. The entropy model is pre-trained on the training dataset to basically learn the probabilities of the next byte, similar to a simple language model like the causal attention model that we talked about earlier in the video. This is a very small model because the goal is not really to use it as a generative model. We just want to understand the entropy or predictability of each byte in the sequence. Being causal, the probability of each byte also only depends on the bytes that came before it. And after passing the input training sentence through the entropy model, we will obtain the entropy of each byte prediction as shown here. This image is taken directly from the paper. We are inputting this sentence, Daenerys Targaryen is in Game of Thrones, a fantasy by George R.R. Martin. If you're using word-based tokenization and splitting up by space, you would get this. And if you did subword or byte pair tokenization, you will get this. The entropy method learns the amount of entropy at each prediction stage, plotted in this graph here. Notice how at the initial D, A, and E, the entropy is high because the model has no idea what the generation is all about. And then after N, the entropy drops as the model begins to guess that you might be talking about Daenerys Targaryen, making the prediction space relatively more predictable and the entropy slightly lower. And then again, when you predict G, the entire next portion of Game of Thrones is more predictable again. Similarly, at the end, after G is predicted, the name of the author, George R.R. Martin, is also low entropy. This graph basically shows where in the input sequence portions of high uncertainty and low uncertainty lies. Can we use this information to group multiple bytes together into patches? Well, absolutely yes. The paper proposes two approaches to use these entropy distribution to find relevant patches in a sequence. The first is a global constraint method where they set an hyperparameter such that entropies below that value will be patched together. In this diagram, look at this red line. Bytes below this red line are predictable enough that we can treat them as a single patch. Bytes above this red line are high entropy, less predictable, and we want them to treat as individual tokens. The second approach is monotonic constraint. Basically, here we look at whether the entropy of a specific byte has increased or decreased after the previous byte. If it has decreased, then we bundle them up with the same patch as before, and if it has increased, we create a new patch. And as you can see, both entropy and entropy plus monotonicity patches up multiple bytes together in areas of high entropy. It increases the granularity of these grouping by essentially behaving as a character tokenizer in areas of higher entropy. And in areas of medium entropy, it kind of behaves like a subword or even a word tokenizer. And in areas of low entropy, it often behaves as an n-gram tokenizer, clustering multiple words inside the same patch. So do you understand what just happened? Remember that these patches will get inputted into the real language model, meaning from D, A, E, the model will try to somehow generate the patch representing Daenerys Targaryen. In areas of high uncertainty or high entropy, you are dedicating an entire transformer token to it. And in areas that are more straightforward to predict the next token, given the previous information, you are predicting it in a bulk through just one large language model forward pass. Also notice that if the sentence was slightly different, like Emilia Clarke plays Daenerys Targaryen in Game of Thrones, Daenerys will now be tokenized differently because the entropy of Daenerys in this position of the sentence is lower because the information that Emilia Clarke plays this person is already present. The same words or phrases are tokenized differently depending on its uncertainty. This was not possible with Subword Tokenizers because Subword Tokenizers, they don't look at the sentence at all. But with entropy model, you are basically trying to dynamically allocate the amount of compute the main language model spends depending on the entropy distribution. Higher difficulty regions means the entropy model will split the sentence into smaller lengths, and lower difficulty means it will group them into larger chunks. And this also allows us to reduce the length of the overall sequence that the language model will see, because more often than not, sentences are very predictable once you know some information about it. And this reiterates the fact that patches scale better than tokens, because on average the sequence length of patches will be much smaller than the sequence length of tokens. We will talk about this idea a little bit more towards the next section of this video, but I hope you're able to get some intuition about why this is the case. Feel free to rewind and rewatch this section of the video because it is definitely one of the more unique and non-trivial concepts proposed in this paper. But if you're happy with all of that, the next thing to discuss, of course, is how do you embed these patches after they are extracted, and after embedding them, how do you pass them through a large language model, and after passing them through a large language model, how do you convert it back into a byte stream? Well, to answer this part, we have to look at the last remaining piece of the puzzle, the word latent or latent transformer. If you've made this far, you've made a lot of progress. You have the understanding about the what and the why of the paper. This paper is trying to propose a method that can dynamically group multiple bytes of a sequence into a single patch and allocate the transformer's compute depending directly on the complexity of the input sentence. No need to create a vocabulary and tokenizers. You learn the tokenizations on the fly with the Entropy model and retain all of the great advantages with multimodality, multilinguality, and the universality and the simplicity of byte-based encodings. You have understood the what and the why so far. And in this section, we'll talk about the how. How does the language model create these patch embeddings and generate a byte stream from these patch embeddings? Let's take a look at that. The word latent typically means a hidden and undiscovered energy. In the context of machine learning, latent space typically means a compressed lower dimensional representation that captures the essential information of your original higher dimensional input. If you know about autoencoders, or if you have seen my video on exploring latent space, a common way this compression works is by an encoder-decoder model. Let's say you have millions of images of shape 512 by 512. The encoder model will generally compress these images into a much smaller one-dimensional vector, say a 100-dimensional vector. And then the decoder model reconstructs the original image back from this 100-dimensional vector. This compression and expression captures the essential features about the images inside this latent space. In the aforementioned video, I showed how you can move around in the latent space and how tweaking certain values in this small dimensional vector space can generate new but similar images. BLT2 has this encoder-decoder architecture. Here's an overview of what this architecture looks like, and we will take a deeper dive into the individual components soon after I describe it from a bird's eye point of view. So we have three more neural networks: the local encoder, the latent transformer, and the local decoder. The local encoder inputs the byte sequence and the information of where the patch boundaries exist as we obtained from the entropy model, and then generates a new sequence of patch embeddings. This can be considered a type of a latent space because you're transforming the originally long input byte sequence into a much shorter representative patch sequence. Next, the latent transformer will basically be a standard transformer-based language model similar to the next word prediction models we talked about earlier. There is almost nothing new to add here other than some implementation details that you can read in the paper. It is a causal masked attention model that inputs a sequence of patches and tries to predict the next sequence of patches. The reason it is called latent transformer is of course because it operates on the patch space instead of the byte space directly. Finally, we have the local decoder model, which essentially reverses what the encoder did. Just like in an autoencoder, the decoder expands the latent space back to the original space, meaning that the local decoder in the BLT inputs the sequence of output patch embeddings from the latent transformer and unroll that into a sequence of bytes. The architecture behind the latent encoder and latent decoder are practically the same, just with reversed roles. So just understanding one very thoroughly would help you understand the other. So let's talk about the final puzzle, the local encoder. As I said previously, the goal of the local encoder is to input the raw byte stream and the entropy predictions from the entropy model, and then output a group of patch embeddings. They do this by using a classic transformer tower containing alternative causal mask attention layers and cross attention layers. Importantly, the local encoder is a much smaller transformer network than the latent transformer model. So even though it does operate directly on the entire byte sequence, it has still very few layers, so it is still not super computationally expensive. Let's look at what it does step by step. First, we have the byte embeddings. The simplest way to get byte embeddings is, of course, to train an embedding matrix or lookup table of the 256 possible values and then replace the byte with the specific embedding. If you remember, this is how we were doing it when we were using token embeddings like Subword Tokenizers earlier in the video as well. The authors also propose another optional approach where they basically take the n-grams of the last few bytes together and add them up using a special hashing function to obtain byte n-gram embeddings. This approach tries to model each byte both as an individual and also as part of different n-grams. Next, we need to convert these byte embeddings into patch embeddings. To do this, first we generate an initial set of patch embeddings using the patch boundaries obtained from the entropy model. This is done by simply pooling from the bytes corresponding to the patch representations. This pooling operation can be max pooling or average pooling or anything else. Basically, all the byte embedding vectors from a particular patch are combined to form the initial representation of the patch embedding vector. Now that we have both our patch embedding vectors and the byte embedding vectors, it is time to apply cross attention to further contextualize the patch embeddings. Now, you might wonder, why do we even need to apply attention to the patch embeddings anymore? We have already obtained the patch embeddings by pooling the corresponding byte embeddings, right? So we can just pass those into the latent transformers and just call it a day, right? Well, yes, I believe that could also work, but the advantage of applying attention also needs to be appreciated. You see, when we apply cross attention between a set of query vectors, which in this case are the initial patch embeddings, and a set of key vectors, which are the byte embeddings, what we are essentially trying to do is find a way to combine the byte embeddings by first learning which byte embeddings are important and how important they are towards the final patch representation. You see, when we do average pooling, we literally average all of the byte embeddings by treating each byte equally important for that patch's embedding. Attention first scales each byte embedding and then adds them together, meaning it's a weighted average where the weights are learned given the patch and the byte inputs. Also, the cross attention only combines information of a specific patch from its assigned bytes, so it is very much still scoped by the patch boundaries. If you're unfamiliar with how attention works, I will again recommend watching these two videos, especially where I explained it from basic first principles, and that should help. Coming back, each cross attention layer is then followed by a causal masked attention layer that updates the byte embeddings. Again, as a reminder, causal masked attention just contextualizes each byte encoding with all the bytes that came previous to it. Basically, instead of taking the entire previous sequence of bytes, you only take a short window of bytes to contextualize them. What this essentially means is after each block causal masked attention layer, the byte representation gets more and more contextually aware about the bytes that came before it, even beyond the patch boundaries. Still, it does not attend to the entire byte sequence globally and only on a fixed local window, and this is the reason we use the term local in the local encoder. After each block attention layer, we once again update the patch embeddings using cross attention. Note that how the resultant patch embeddings from the second layer onwards also gets more and more enriched because they learn to attend to more and more contextually aware byte embeddings. The final result of the local encoder are two things: the final contextual byte embeddings and the final contextual patch embeddings. The patch embeddings, of course, go into the latent transformer model where we use causal attention, and we learn to predict the output patch representations given the input patch prefix representations. The latent transformer uses full global level causal attention by attending to the entire patch sequence. So the local encoder is a shallow and lightweight model that uses local attention but on a larger byte sequence, and the latent transformer is a much larger and a heavier model that uses global attention but on a shorter patch sequence. I hope you're understanding the big division of labor here. Finally, the local decoder must then convert the output patch sequence back to a stream of bytes. The input to the local decoder is once again the patch embeddings coming out of the latent transformer and the contextual byte embeddings of the last layer of the local encoder network as well. These byte embeddings form the initial set of byte representations, and we will apply cross attention to contextualize these initial byte embeddings with the output patch embeddings. We once again apply a series of cross attention and causal attention layers to contextualize the byte embeddings. This time the byte embeddings acts as the queries and the output patch embeddings acts as keys. You are continuously contextualizing each byte embedding with the information generated by the latent transformers and then converting it back to a probability distribution between the 256 possible byte values. Finally, the entire network is trained end-to-end using next byte prediction, such that the next byte is predicted given the input prefix. Because the entire approach is causal in nature, like none of the models, the entropy model, the local encoder, the latent transformer, and the local decoder, all of these models use causal masked attention and they never looked at future tokens while generating the next byte. The network is therefore still completely causal, and we can use it to generate text autoregressively during inference. How cool! Listen, I know you probably still have questions. My goal with these videos is not really to be an alternative of reading the paper, so you should go read the paper now. I just wanted to give you all the tools and the knowledge and the background information that I found useful when I was reading this paper, so your experience will be easier and less challenging. So even if you think you've understood this entire video, I'll still strongly urge you to go read the actual paper, because there are a lot more details and you'll find some interesting sections, like the results sections is pretty interesting and we didn't get to talk about it. And as always, if you have questions afterwards, do post them in the comments. I'm usually very happy to see them. That's been my time, people. This was a pretty long video with a lot of information. I hope you had fun watching it. Goodbye. Stay magnificent.